This program is brought to you by Stanford University.
Silence can be a pleasant experience. Imagine standing in the middle of the Utah desert on a warm summer day. It's quiet, it's warm, and it's relaxing. Now imagine you're born deaf. You cannot hear. You cannot communicate by spoken words with your friends, with your family. Life has only recently got better for hard of hearing patients with the development of modern hearing aids and cochlear implants. But with new technology, also new challenges arose. Our ears have only evolved to respond to sound with very high sensitivity and high selectivity. They have not evolved to tolerate some of the man-made sounds that have very unusual and unnatural physical characteristics. These sounds are, for example, explosives, industrial noise, musical instruments, power tools, and headphones. The rise time and the peak energy and the sustained duration of some of these sounds are highly detrimental to our hearing. In addition, some modern drugs, chemotherapy drugs, as well as certain antibiotics, are hazardous to our hearing. This, in combination with the effects of aging and with genetic disposition in some instances, can cause a worldwide pandemic, and this is what we're currently experiencing. There are about 350 million people all over the world that suffer from disabling hearing loss. At the center of our sense of hearing is a very interesting cell. It's called the hair cell. These hair cells sit deep inside your brain, and they are enclosed by a very dense bone. They have nothing to do with the cells that are on your head, with the hairs on your head. These are modified neurons. And the name-giving part for the hair cell is a so-called hair bundle. It's a protrusion of the cell sticking out of the apical surface and bathing inside the inner ear fluids, where they become stimulated by sound waves and by acceleration forces. This conversion from a mechanical energy into chemical energy can be nicely visualized when one fills a hair cell with a sensitive dye that responds to calcium ions that influx into the cell. And this happens here at the top of the hair cell, where there's a probe attached, and it moves the hair bundle to the right side. And whenever it pulls on it and moves it to the right side, you can actually see this flash of ions that enter the cell. This is visualizing the process of conversion of mechanical energy into chemical and electrical energy very nicely. Many labs around the world are interested in finding the molecules and the molecular components of this transduction machinery. And as I will explain in a second, there are many reasons why this sense hasn't been really elucidated at the molecular level. But I want to mention one other thing. I mentioned deafness and the issues with deafness. Hair cells that are inside your brain are very scarce. There are only about 12,000 to 15,000 in a human cochlea, and they do not regenerate. So once they are lost in response to a toxic sound or to an antibiotic, once a cell is lost, it cannot be regenerated by natural means. Therefore, over time, you constantly and gradually lose your hearing, and it cannot come back. It's incurable, and that is one of the major points why deafness hasn't gotten a cure yet. So the 2 points of interest of research are: how does this work, this conversion of mechanical energy into electrical energy? And secondly, how are we able to bring back lost hair cells to cure deafness? I want to illustrate one of the reasons why it has been so difficult to get a grasp on hair cells in the inner ear. Our brain has 100 billion neurons. This was a huge number for me up until 2 weeks ago. Besides these 100 billion neurons in the brain, there are 12,000 to 15,000 cochlear hair cells. If you if you transfer this ratio to a city like New York City with 8 million people, if these 8 million people would correspond to the number of neurons in the brain, the equivalent of hair cells that you can get out of a single cochlea would be the equivalent to one person walking down 42nd Street. Another comparison, for a meaningful drug screening assay, I would assume you would need about 1 million cells that you can grow easily in a standard cell culture dish. To fill this culture dish with inner ear cells, you would need the equivalent of 40 experimental animals. I think this is not only very impractical, it's actually not ethical, and I would not be able to look into the eyes of my dogs when I go home at night. So we needed to come up with another source, with a renewable source for inner ear cell types. And we turned our attention to stem cells. Embryonic stem cells can give rise to every cell type in the body. And we thought maybe there's a way of suppressing all the other organs that are developing in the body, and at the same time enhancing the formation of ear cells. So how do we do that? We learned from development. The body, the mouse or the human or any other organism already shows us how to make an ear. We just have to look carefully. And if we look, we can see the early signs of ear development start with a thickening of the outer layer of the embryo. And this layer is called the ectoderm. So this surface layer thickens at an early stage in the mouse after 8 days of development. And shortly thereafter, this thickening of the outer surface is dimpling in, is invaginating. And this dimple is later forming a vesicle, a round ball that goes on and forms the ear. So there are 3 things we can learn from this. One is the ear develops from the surface layer of the embryo. So we need to get embryonic stem cells to form surface cells. The second one, there are many genes that are already expressed and present in this dimpling, thickening of the outer layer. And one of them is shown here. In red, it's a gene called PAX2. And PAX2 is very important for ear development. If you lose it, your ear doesn't form correctly. Many of the cell types are missing. Therefore, we think PAX2 is a very important marker that we can use for our studies. A third finding comes from experiments done by a colleague who took the ball, the otic vesicle, and he transplanted it from the embryo, from the ear region, to a limb. And what he found is that all the major cell types of the ear develop no matter what environment this ball has been transplanted. This means the cells that are red here have all the information to form the major cell types of the inner ear. So we strategized and we thought maybe there's a way of just generating these PAX2 expressing cells. The way we did this is we coaxed embryonic stem cells first to develop into the surface layer. And then we looked what other people have found about ear induction and how the ear forms. And there are certain proteins, there's a group of growth factors called the FGFs. And when we add these growth factors to the surface layer of cells, we can see that they upregulate in a dramatic fashion this PAX2 transcription factor. So what can we do with these cells? One experiment a postdoc of mine did was he took these cells and he injected them back into an ear, into the otic vesicle at the stage where we think the cells are in development, namely in the stage where all the cells are PAX2 positive. And he used a chicken embryo. And I mentioned that the ear develops from a little ball, and then we let the ball develop into a fully grown inner ear. And after that happened, we just took a slice, and we were looking for the mouse cells, the mouse embryonic stem cells that we had coaxed into early ear cells, whether they are able to form ear cells. And what you can see here is in green are the mouse cells. And all the other cells surrounding the mouse cells that are not green are chicken cells. And in red is a hair cell marker that labels sensory hair cells. And the the yellow color is the composite color of the green and the red. This means that the yellow cells on the right side are hair cells that are mouse hair cells, but they are in a chicken inner ear. So what have we learned? I think one thing we have learned is that we can generate from embryonic stem cells, which is a renewable source. So we can make as many cells as we like, as long as we have large enough incubators. We can generate hair cell-like cells, cells that look like hair cells, that express genes that hair cells have. They also have some functional characteristics of these cells. They don't look perfect. And particularly if you compare them with hair cells that are present in the mammalian, in the human, and in the mouse cochlea, they are a little away from perfect. This is an example on the bottom of a native cochlear hair cell. Another interesting thing we learned is by applying other technologies and combining them with this technology, we are now able to find proteins and genes that are right at the correct location for being part of the transduction machinery. This is what I mentioned previously. We don't know a lot about how the mechanical stimulation is being converted into chemical and electrical energy. And this is one of the new findings that we have, a protein that is right at the tip of these hair bundles, right at the correct place. So I think the future will tell us a lot. I think in the next decade, we will probably know how these cells really work, and the ear catches up to vision and smell and taste in that regard. But there's more. Being in a medical center, we always wonder where does this research lead us? And I'd like to illustrate this here. I think there are two pathways that we are going right now. On the top, you see the human organ of Corti, which is the place where the hair cells are located in the human cochlea. And the hair cells are these darker blurbs that are in there. And after a toxic insult, they're gone. This is what the inner ear of a person who is deaf looks like. There's a single cell layer of a damaged cochlea. Now, with stem cell technology, there are two pathways that are imaginable. One is shown on the left, which is cell transplantation. And we have shown that at a very rudimentary stage in the chicken embryo, where we transplant cells that have the ability to repopulate these single cell epithelia, and then hopefully lead to an epithelium that has reseeded hair cells that at some point, hopefully for a patient, will be able to hook up with the nervous system and work properly as the original cells were. The other pathway that I think is very promising is now to use stem cell generated cells in culture dishes and use them for high throughput drug screening. Now we can test hundreds of thousands different drugs without killing so many animals. In fact, we don't have to kill any animal for this kind of research because we do everything in a test tube. And once we have positive candidates, we can apply them to the same pathway shown on the right and hopefully get regeneration. And I think this is the goal of my lifetime, at some point being able to reach the bottom, so very egoistically that I'm not turning deaf at some point. Taking me out of the play, there are other people out there that this technology can really help. So this is quite motivating, and I'm very glad being in a place like Stanford where there's a lot of collaboration going on, where we can really achieve this kind of goal. Thank you.